Okay, so YouTube, in this video, I'll be using residue theory from complex analysis to solve this integral. So, to start off with, you can sort of transpose this into the complex contour integral. Like so. And we can draw a contour to match that. So you can say that we have points here. We draw a semicircle. I'm not good at drawing semicircles, but bear with me. And then that would have the contour C. Or this would be the contour C. And here, what we plan on doing is taking the residue of this, using the residue theorem to solve for this integral. So to start off with, to make this easier, since cosine of z is kind of difficult to work with, we can say that e to the iz power is equal to cosine z plus I sine z. So if we take the real part of e to the iz, we get just cosine of z. So essentially what this is saying is the real part of this entire integral, of this integral at least, is equal to the original one that we had from earlier. This statement is true. So now we have something that's quite a bit easier to work with. And now we can start working with the poles on the bottom. So the bottom is going to be z squared plus 1 squared. Then we can factor it out. So we have z plus I squared, z minus I squared. So then we have the poles negative I and I. And both of them are poles of order 2. So pole order 2. So since we created a semicircle, only the top half of the plane is going to be included in this contour. So since we have negative I as our point of discontinuity or hole, it won't matter because our contour only takes the top half. So we'll have I somewhere here. So when we're taking our residues, we're just going to exclude negative I, pretend it doesn't even exist. So now let me just erase this here. Okay, so now if we take the real of this integral here, this is equal to the real of 2 pi I times the residue of e to the iz. Sorry, this would be the residue of iz, z squared plus 1 squared. Okay, let me just get rid of this. So okay, and remember the integral we're trying to solve in the first place is this. So it should be completely real since we never mentioned anything imaginary. So just crazy how you can incorporate all this complex analysis, complex stuff, and you should end up with a real solution. So let's continue on with this. So we know that the holes or the poles that we will be working with is going to be z equals I, since we're excluding anything in the lower half of the plane. So if we're drawing our graph out, this is going to be the real, this is going to be the imaginary. Negative I is going to be in the lower half, while positive I is going to be in the upper half, so we're only going to take into account this one. And so here, the residue of e to the iz respect to z squared plus 1 squared with respect to I, that's going to be equal to the limit as z goes to I of 1 over So the order of our pole is 2, so that would mean n equals 2. So formula is n minus 1 factorial. Then you take the derivative, the n minus 1 derivative of the function that you have. So the function we have in hand is this times z minus I squared. So we have this entire jungle mess. We know that n equals 2, so this just ends up being 1 because you have 1 over 2 minus 1 factorial. That's 1 over 1 factorial, which is just 1. So this doesn't even matter at all. And then here we have n minus 1 again. So in actuality, it's not too bad. We're just taking a first derivative. And then we know that z minus I cancels out with the z minus I in the denominator. So we end up with z plus I here. So this all reduces to the limit as z approaches I of the first derivative of e to the iz over z plus I squared. See, not so bad. And then we differentiate this using the quotient rule. We'll end up with I e to the iz times z plus I squared minus e to the iz times 2 z plus I over z plus I to the fourth. And then we take the limit as z approaches I. So then this will equal I e to the I times I negative 1 times I plus I 2I squared. That's negative 4 minus 2e to the negative 1 because I times I plus 2I because I plus I here over, then we have, sorry, this should be a power, okay, 2I to the fourth power, so that's just 16. So now we get negative 4I e to the negative 1 minus 4i e to the negative 1 over 16. So we get negative 1 over 2e, or sorry, negative I over 2e. Okay, and then we're almost done. So that's going to be our residue. So just get rid of all this. So this thing here, this little term is negative I over 2e. So then this is equal to the real part of 2 pi I times negative I over 2e. So this is equal to real of pi over e, which is equal to pi over e. That is our final answer to the problem. So using complex analysis, we found that the integral from negative infinity to positive infinity of cosine x over x squared plus 1 squared dx is equal to pi over e. Thank you for watching the video.